Collatz sequences are sequential input-output operations. Are the combinatorics of these operations fuzzy or fixed? Are they blurred or precise? To understand Collatz combinatorics, let's tabulate sequences. Given consecutive odd integers as the input numbers in the left column, let's find the first output of each one. We can skip the even numbers. First, we can eliminate the second column completely. This is the second step of each and every sequence. It's the one where you multiply by 3 and add 1. In other words, this operation, 3x plus 1, the other name for the conjecture, is not required for the purposes of determining Collatz combinatorics. For the purposes of combinatorics, we need only consider the odd numbers. In the third column, every other number is the odd output of the input integer. Now that's half of all sequences. Then for the fourth and the fifth column, we can see every fourth and every eighth odd sequence having their first odd output. For sequences 5 and 21, we see the first odd output is 1. There are no intermediate odd numbers. What rules can be deduced from the previous table? Well, there are 3 distinct operations. The first output approaches 1.5. The second approaches 0.75. And the third approaches 0.25. Now, it turns out that these operations are not approximations. They are actually whole number results for every positive integer input, as shown in the next slide. The first operation is precisely n plus 1 times 1.5 minus 1. It applies to every other odd number beginning with 3. Therefore, we can say it applies to every 4n plus 3. These numbers can be described as congruence class n plus 1 is congruent 0 mod 4. And for convenience, we can call this operation A. The second operation is precisely n minus 1 times 0.75 plus 1. It applies to every fourth number beginning with 1. Therefore, we can say it applies to every 8n plus 1. These numbers can be described as congruence class m minus 1 congruent 0 mod 8. I call this operation B for convenience. If you're wondering how 1 can belong to this class, you just need to do the arithmetic. If n equals 0, then 8 times 0 plus 1 equals 1. And also 1 minus 1 congruent 0 mod 8. The third case is different because it seems there is no direct operation for numbers of the form 8m plus 5, such as 13, 21, and 29. We see input 13, output 5, input 21, output 1, input 29, output 11. It appears chaotic. It turns out that one can show there is an intermediate odd number in each case, which is hidden by the odd, even, odd operation. We can say that 3, 5, 7, and 11 are the intermediate odd inputs of 13, 21, 29, and 37. The second output is exactly the same result as you have when the even numbers are included. Now you can see that the intermediate numbers are simply the counting numbers, and that the input and actually even the output is present in a previous sequence in all cases. So there we have it, congruence class m minus 1 is congruent 4 mod 8, and we can call this the hidden operation C. Now we can put it together as an atomic input-output system with 16 states. This diagram shows that the combinatorial circuit is bounded by lower and upper values. Inputs n-1 congruent 0 mod 32 and n-31 congruent 0 mod 32. So you need to understand that this is an infinite series of circuits or gates stacked together, and that the same divisibility rules apply over and over again. We can imagine the combinatorial units joined together in an infinite Turing sequence. So, of course, we can choose a number and see where it goes on the tape. So input 41, output 31, input 31, output 47, input 47, output 71, and then we're off the screen with the next step. Calling this the 41 sequence ignores the obvious fact that it's also the 47 sequence, the 31 sequence, and the 71 sequence, and any other number on that sequence, ultimately ending in 5 and 1. Here we see the repeating input and output operations. They are the same, but their distribution is completely different. For the input, we see the same 4-unit combination repeated infinitely. For the output, we see a 16-unit combination that repeats infinitely. So what is the precise relationship between them? Each of these 16 output states is hardwired according to the input position of operation A, B, or C. You can designate the position of each number using congruence so that n is congruent y mod 32, where y is odd and between 1 and 31. For example, there are 4 operation B inputs, but their outputs are A, B, or C, depending on whether n-1, -9, -17, or -25 is congruent 0 mod 32. Obviously, this is true for infinity, and we can show a tally for each register. It's not going to change, such that A has 3 outputs, B has 3 outputs, and C has 3 outputs. Half of them are A, a quarter are B, and a quarter are C.